Hey guys, this is the last video in chapter 6 about electron configurations. Now it's important to know that before we start electron configurations that when we talked about energy levels in orbitals, those energies for those different subshells are not degenerate. What that means is that for example, the p orbital or the p subshell in the second energy level is not equal in energy to the s subshell in the second energy level. In fact, as we get increasing values of L, we have increasing energies. So much so that after the third energy level, after the 3p, we actually start getting a little bit of mixing with those energy levels. Okay. So how do they fill? How do we put electrons in these things? Well, we have this little picture here, and there's a picture on the blackboard as well, about how we fill this. It goes 1s, then the 2s, then the 2p, then the 3s, the 3p, then the 4s before the 3d. Now there's two different ways to write the electronic configuration for atoms. There's the electron configuration and the orbital diagram. What the electron configuration shows is a number telling us the energy level of this subshell. We have the subshell itself, what type of orbital is it, or what type of subshell is it, what shape is it, and then the total number of electrons that are in that subshell. The orbital diagram is much the same. However, not only do we have the energy level and the subshell, but we have boxes representing the different orbitals. One possibility for S, 3 possibilities for the P subshell, and we put electrons in them using arrows to denote the spin. Remember, 2 electrons in the same orbital must have different spins. And so we have some rules there. Okay. The off-bow principle is for both the electron configurations and the orbital diagrams. We have to fill the lowest energy levels first before we go on. Hund's rule is for the orbital diagrams. Every orbital in the subshell gets an electron first, and then we go back and add other electrons. And then the Pauli exclusion principle tells us that every electron has to have different energies, and so we have to have spins differing for both. Let's take a look at a couple examples. Oxygen and neon. Okay, oxygen is atomic number 8, so it's got 8 valence electrons. So 8 electrons. I'm going to use black for this. Now oxygen so we start with the 1s, and there's 2 electrons that can go in there. And then we have 2s, the 2s subshell, so 2 electrons can go in there. The next subshell is the 2p. Now I've already used 4 electrons, so there's only 4 that can go there. Let's take a look at the orbital diagram for oxygen. So this is the 1s, and we have 2 electrons in there, so we denote that with spins. The 2s, 2 electrons in there, and then finally the 2p. Now remember, every orbital gets an electron first before we go on. So 1, 2, 3, 4. There's the orbital diagram for oxygen. Let's do neon with 10 electrons. 2 electrons, 4 electrons, and then 10 electrons, 2p6. Filled energy level. It's a noble gas, right? It's the noble gas right after oxygen, so it's got to have a filled energy level, and that's what we have. The valence or the orbital diagram, much the same as oxygen, except now we have 2 extra electrons. So the 2p, the 2s, the 1s, 2 electrons there, 2 electrons there. And then the 2p is fully filled, right? No room for electrons. Neon is happy as being a monatomic thing. But what we can see here is kind of interesting, because if we look at oxygen, we know that oxide is O2 minus. If we gained 2 electrons, we would have 10 electrons. And look where those electrons go. We've got one place for an electron and then another place for an electron to fill this 2p subshell and the second energy level, and that's why oxygen gains 2 electrons to be a 2- charge. Now, we don't have to do this for all elements because thankfully, something like, I don't know, polonium with 84 electrons or lead with 82 electrons, that'd be really tough. I mean, that's only 8 electrons. You can imagine 84 electrons would just kind of drag on forever. So we have a shorthand method based on the periodic table. Okay. So here's a picture of the periodic table and the different blocks. If we look, there's 2 columns for the alkali metals and alkaline earth metals. That represents the S block. And there's 2 electrons that go in the S subshell. Over here in the nonmetals, we have 6 columns going from boron to neon in the first row. And if we look at their structure, they all end in p electrons, and there's 6 electrons that can be in the p subshell. There's 10 columns for the transition metals, the D block. And if we look at the D subshell, there's 10 electrons there. And finally, 14 different columns for the F block, the lanthanide and actinide series, and there's 14 electrons that can go in the F subshell. So what does a shorthand look like? Well, we're going to do magnesium and tellurium to look at an example. Okay, magnesium has 12 electrons. Okay, so instead of writing out all 12 electrons, what I'm going to do is go back to neon, its previous noble gas, the one that's right before it. And I see 1s2, 2s2, 2p6 is representative of neon. So what I'm going to do is I'm going to say all those electrons, we'll go ahead and write it out first so you can see what I mean. Magnesium 1s2, 2s2, 2p6, that's 10, 3s2. There's my electron configuration for magnesium. This right here is the same as neon. So what we can do is we can say those core electrons are represented by neon, and then we have 3s2. We can do much the same on the other side of the periodic table. We can do much the same on the other side of the periodic table. However, it still has to be the previous noble gas. We can look at tellurium or selenium or any of the other ones. Sulfur would actually probably be a little bit easier just because I'm going to write it all out. So sulfur has 16 valence or 16 electrons total. 1s2, 2s2, 2p6, 3s2, 3p3. Now, argon is really close to sulfur, but we can't do that. We have to represent core electrons with the previous noble gas. And so there's that. And so this is represented by neon. And we have 3s2, 3p3. And we can do that with any element on the periodic table, the shorthand method. Now, I said valence earlier. We're getting into valence electrons and what those are. Valence electrons, there's 2 parts to the valence electron idea. It's the highest energy level. So highest energy level plus any unfilled lower orbitals or subshells. Any unfilled lower subshells. Okay. All right. So let's take a look at, so for, sulfur in group 5, we already know it's got 5 valence electrons, but we can definitely see that the 3rd energy level is the highest energy. So all these are core electrons. The valence electrons are these guys right here. The highest energy level, 3s2, 3p3, that's 5 valence electrons, which is what we see. Now, for something like iron. Okay, iron has an atomic number 26, so it's got 26 electrons. Let's take a look at this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then the rest of it goes to the 3d. So we have 3d6. So that is the, if we look at this, that's 10, there's 20, there's 26. That's 26 electrons. Now the valence electrons for a transition metal are a little different, because we say, okay, all of these guys are core electrons because we have the fourth energy level. So we have the valence electrons that are from the fourth energy level to the highest energy level, plus any unfilled lower subshells. Okay, valence electrons. Notice again that the 4s filled first. We can just take a look at the periodic table, and we can come up with a very nice way to shorthand these things. So look at titanium. Titanium's previous noble gas is argon. Now we go to the fourth row. These rows represent energy levels. 1, 2, 3, fourth row. So that's going to be 4s2. And I know the 3d comes after the 4s2, so this is 3d1, 2. Quick and easy shorthand using the periodic table. Finally, we have to talk about a couple of anomalies. Chromium's group and copper's group. Okay, chromium looks like this, or would look like this, I should say, if we just filled it normally. 4s2, 3d4. Much like copper would look like this, 4s2, 3d9. However, they both do the same thing, and the reason is because fully filled and half-filled subshells, so 5 and 10, are relatively stable. So what chromium and copper do is they promote one from the 4s into the 3d, giving us a half-filled orbital for the d subshell for chromium and a fully filled subshell for copper. If we look, the 3d, look at the orbital diagram. 1, 2, 3, 4, 5 orbitals. What I mean by half-filled is we have 1 electron in each of those orbitals. So that's some anomalies with electron configurations, and that's actually where we're going to end the videos for Chapter 6. Hopefully this made a little bit of it more clear, because you can go back and take a look.